Hi, imagine you run a popular web application with lots of users. Now assume each of these users is allowed to make too many requests at once. Your system could either slow down or crash. So hereby comes the concept of rate limiting that helps controlling how many requests each user can make in a certain time, keeping everything running smoothly. It's not just for web applications, but there are many use cases like, let's say, email services use it to prevent too many emails from being sent at once. Also tools like web crawlers that gather data from websites needed to avoid overwhelming the site with requests, and many such areas. So in this video we'll explore types of rate limiters and how to design one that works well in large systems. So let's get started. Starting with the types of rate limiters, we have four types of rate limiters: token bucket, leaky bucket, fixed window, and sliding window. So starting with the first one, what token bucket rate limiter is. So as seen in this image, a bucket holds tokens and each request consumes one token. If the bucket is empty, requests are denied. And these tokens are refilled at a fixed rate. So you can see here the refiller as well, which contains three tokens. When 5 of these requests are sent, then 3 requests gets passed along with these 3 tokens, and thereafter the tokens get empty, resulting to dropping the remaining requests. Next comes leaky bucket. Similar to token bucket, but instead of consuming tokens, requests flow out at a fixed rate. Excess requests are either dropped or queued. So here, according to this image, we have 5 requests, and those 5 requests when are passed, then it first checks is there enough space in bucket. If yes, then the requests are forwarded to the queue, and then the queue will process this request at a fixed rate. And if no, if the bucket is full, the additional request will be leaking. That means the additional request would be dropped. After leaky bucket comes fixed window. So what fixed window is, it limits the number of requests within a fixed time window, like let's say 1000 requests per minute or so on. So in our case, according to this image, like let's assume for 1 minute we have a limit of 3 requests. So if there are additional requests apart from 3, then those would be dropped, and if there are requests under 3 or 3, those would be accepted. So you can see here at time 1 there were 3 requests, so they were accepted. At time 1 there were 4 requests, so 3 were accepted and 1 was dropped. So similar is the case with 1 3 and 1 4. So this is how fixed window work. Going forward to sliding window. It is similar to fixed window but more dynamic. It uses a sliding time window to average out requests. So consider this image and assume that we have a sliding window of 4 requests per minute. So it will check that how many requests were made in the last 1 minute. If that exceeds 4, then the additional request would be dropped. Otherwise, the other requests would be accepted and would be processed. So these were the types of rate limiters. Now let's move ahead towards the high level design of rate limiter. It's very simple. Rate limiter rules are stored on disk as shown in this image on the top, and there are some workers that frequently pulls their rules from disk and cache them for faster access. Now there is a middleware which fetches rules from the cache, retrieves data like timestamps and counters from Redis. When a request comes in it computes whether to process or rate limit the request. So if the request is processed, then you can see the success in green line, which goes to the API server, which is a request that is processed, and the other thing that is it is not accepted. If the request is not accepted, we have two options. One is to drop the request and return a 429 HTTP status that says too many requests, and the second is to push the request to a message queue, process it later. Now while scaling, we might face a challenge that is a race condition. So let's say if there are 2 threads which read the same counter value from Redis, example let's say 4, and both incremented without coordination with the counter, it could be incorrectly set to 5 instead of 6. How to prevent it? We can use Redis Lua scripts to perform atomic operations and avoid locks, which could hurt the performance. The second step is synchronization, which I don't prefer, but let me tell you what happens in synchronization is it uses sticky sessions that route traffic to the same server, but it isn't that much scalable. So better not to use that and use Redis Lua scripts to perform atomic operations and avoid lock. So yeah, that's it.